Okay, so next part we are looking at the roots of unity. So suppose that z to the power of 5 is equal to 1, where omega is the roots with the smallest positive argument. That's better. Roots of z with the smallest possible, z to the 5 with the smallest possible argument. Show that 1 plus omega squared plus omega cubed plus omega to the power of 4 all equals 0. So this sort of question here, it's called roots of unity. It's a really interesting concept. The way in which we're going to show this is, firstly, we're going to find out what all the complex roots of z to the 5 are, and then we're going to algebraically show that this property over here is true. Once we've done that, then we'll have a look at what it looks like graphically to prove to you, or to actually show to you that this is the case. So first thing we need to do is we need to find the roots of so this part over here, we can speed run it now. We have z to the 5, and it's equal to 1. In polar form, that's going to be cis 2k pi, where k is just an integer number. And yeah, then using de Moivre's theorem, we know that the roots are going to be cis 2k pi all over 5. And what values of k are we looking at, Mr. Leishman?
Let's do 1, 0 through 4.
Bingo. So, putting this in, let's find the roots. So, we say up, we come to our calculators. And I'm going to do the slightly lazy person's way of doing it. And I'm going to say, let's go 0 into alpha k. So I can just change the value of 0 there to get my roots inside. And then let's import 1 cis, whatever the argument is. So 1 shift, use the phasor symbol for cis, and then it's going to be 2 alpha k pi all over 5. And first root, lo and behold, is 1. No surprises there. Next root, go up, and we change it to a 1. And what do we get? Nothing pleasant, so let's just say 0.309. Plus I 0.951. And then, next one, we're going to go 2. Slightly different. So we're going to go 0.809 or negative 0.809. Comma plus I 0.50588. And then I'm going to go 3, but I don't really need to, because without hitting execute on this, what will the value of k equals 3 give? Any ideas?
The negative.
Yeah, it'll give the negative version of this guy, so it will be 0.309, I believe. No, sorry. It's this one here, the last one, but the conjugate. And then k of 4 is going to give us the conjugate of this guy here. But we could predict that, couldn't we? Alright, the other way you could state this in exact value is you can go 1, comma, cis, and that's going to be 5 over 2 pi, comma, cis, 5 over 4 pi, comma, and so on, and it will give you all the roots for that. Okay, so that's the first part done. We've found all the roots for this guy. Next thing we want to look at is, how can we prove this property here? Oops. There we go. All right, proving the property, or showing the property, sorry. Given 0 equals, we'll do the other way, 1 plus omega plus start off with the left hand side, 1 plus omega squared plus omega cubed plus omega to the 4, where omega is going to be what? The first root with a non-zero positive argument. So it's this guy here. Can we see that from the definition?
Yeah.
The first smallest positive argument. So this guy over here, this is omega. So what this means is that omega is going to be cis 5 over 2 pi. Hence, if we sub this into this argument here, on the left hand side, it goes 1 plus cis 5 over 2 pi plus cis 5 over 2 pi squared plus continued all the way to cis 5 over 2 pi, all the way to 4. And we throw that in our calculators and then have a look what we get.
Would anyone like something from Cafe again?
Not today, sorry ladies. Thank you. Okay, so let's throw that in our calculator. We go 1 plus. In fact, we'll make our life a little bit easier. Let's store omega in a macro. We will store it in, we have W? Yeah, we got W. We'll store it in W. So we'll just type in 1 cis, then 2 pi over 5. And there we are in, oops, wrong button. Alright, there we go, happy as Larry. We've got that in our macro. So if we put this in for the left hand side, 1 plus omega plus omega squared plus omega to the power of 3 plus omega to the power of 4. What do we expect to see here? Have a think. 0. But the question is, why does that even make sense? De Mauvoir. It's the tools he gives us to do it. So let's think about this geometrically, guys. Well, firstly, let's just finish this off. Showing. Let's just finish this off. The fifth root of this guy is going to be, 1's going to be out here, One's going to be sort of there. Another one's like there, there, and there. Do we agree with that?
Yeah.
Because they're equally spaced by 2 pi over 5. This guy goes out to 1. Now all of these vectors have the same length of 1 unit in length. But this guy over here, it's 1 unit in length and it points out to omega. And this one is going to point out to omega squared. Because remember, omega is the first one. Second one we said was omega squared. This would be omega cubed. This would be omega to the power of 4. And that would be omega to the power of 5 if we really wanted to. The thing is, whenever we're multiplying complex numbers together, when we're doing it in polar form, it's a lot easier to see. But do you remember if we multiply, let's go 2 cis 3 times 4 cis 5. Do you remember what happens? Where you go
The
2
times and then the arguments get added.
Yeah, the moduli, they multiply together, so they dilate, and the arguments get multiplied together, added together. So they translate or rotate in terms of what it does to the vector. So the multiplication of two vectors, it causes a dilation in the length of their moduli, and it causes a rotation in terms of their argument, or the way in which they're pointing. So if you think about it, if you square omega here, it's causing a dilation, but how long is that vector anyway? It's 1, so it doesn't actually dilate, it doesn't change. But if it was non-zero, it would. So we don't change it, but when we're multiplying it by itself, what happens in terms of its direction it's pointing? It rotates by how much?
It's 2 times by its own.
So it rotates by the definition of its argument here. So if there's a rotation of, from here to here, if there's a rotation of 2 pi on 5, when you're rotating because you've squared this guy, you're going to get another rotation of 2 pi on 5. So all we're doing is we're adding 2 pi on 5 every time we square this first value of omega here. And that's why this is omega, that's omega squared, that's omega cubed, and that's omega to the 4. Can we see why these are now?
Yeah.
Okay, now here's the next piece of information. The question is, why does that property stand? Let's think about it. Firstly, this over here circumscribes a circle, if we wanted to, roots of unity. Let's have a think. Let's get this verse vector here, and we'll just draw it outwards, and it's 1. Let's get omega here, and we'll add it to the 1. So head to tail, which way is it going to go? Up. Omega squared.
Are we doing pentagons?
Do you see when you sum all of the roots of the unity together?
Back to the origin.
Yeah. So it starts off here and you're just describing a circle again. So 1, that's omega, omega squared, omega to the 3, omega to the 4. And of course, you need to get a new pen. You're circumscribing a circle there. Sound okay?
Yeah.
So this, nailed it. This is the concept of roots of unity. So the concept is that the first, the first positive root, the root with the first positive argument of what we're working on here can be defined as omega, and it has the property such that if you add all of the roots together, it will give you 0, where all of the other roots can be defined by simply squaring the first root that has a positive non-zero argument. Happy? Awesome.